everyone, welcome to the final bit of nuclear physics with Dylan, teachers, science, and your boy Dylan. Today I'm going to be learning about binding energy. I actually had that written up and I deleted it for a stupid reason. Binding energy is essentially the energy released from mass that is converted to energy during a nuclear reaction. That's all it is. It can also, not for only nuclear reactions, other bits of physics, but for now let's just assume it's just nuclear reactions. So this is how you do it for nuclear reactions. So I think we've all heard E equals mc squared here. That is Einstein's formula that determines the amount of energy equals the speed of light squared, c is the speed of light, by the mass defect. So the mass defect that goes at the speed of light squared is converted to energy. So essentially, this is what's happening during this equation. Let's say I know I've got tritium plus, bear with me. So we've got this fusion equation. So what we're doing is this, and essentially this is our equation. So now what we do is we calculate the mass of this side. We basically, to calculate the mass defect, so we calculate the amount of protons and neutrons on this side. Calculate the mass of the protons and neutrons only on that side. So, and then you've got c squared. So basically now what we do is this. So once we calculate that, I'm just going to put up some numbers. You might want to copy these down for the whole thing, just saying. This is a proton, a neutron, and an AMU, atomic mass unit. One atomic mass unit equals 1.661 times 10 to the negative 27 kilograms. Please write these numbers down. You will need them. I guarantee you, if not, I promise you, you will need these numbers. Unless you can remember them in your head, by all means, go for it, genius, but you probably want to write these numbers down. Also, there's one more. 1 electron volt equals negative 1.6. So make sure you've written this number down at the bottom. 1 AMU, blah, 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 blah. Pause it and write that down. 1 EV. So an EV is an electron volt. We'll go through what that is a bit later. Is negative 1. It's 1.6 times 10 to the negative 19 joules, and that is 1 electron volt. Okay, now a neutron's mass in kilograms, and I have this written in one of my notebooks because I actually don't remember this either. I have it written down in a notebook. So if you guys want to bear with me for 1 second as I shouldn't take too long, I hope, and then I shall grab this notebook and we shall begin the mathematics. There's a lot of maths in this chapter, I warn you now. A lot of scientific notation that will be in this chapter. A lot of maths in this chapter. So the mass of a proton is 1.67252. So this is the actual equation we'll be calculating, by the way, but I just need some room. I'm assuming you both got the two numbers before. So the mass of a neutron and the mass of a proton. The mass of a proton is 1.67252 times 10 to the negative 27 kilograms. And the mass of a neutron is 1.67483. So neutron is slightly more. Actually, more? I think it's less. I don't know. Times 10 to the negative 27. 10 to the negative 27. So these are both in kilograms, okay? There you go. That's the mass of proton and neutron. I've got it written in my notebook, so I'm going to be copying from that since this whiteboard's too small. So yeah, you guys might want to copy this down. I've got these written down as well, because I'm not going to have room to write all this and then start doing proper calculations. We could be here for a good 5 minutes, 5 minutes doing one question. Not that way. I'm just going to write this again at the top in a nice small one at the top. H becomes helium and a neutron. Right, there we go, that's at the top now. Now, first thing we need to calculate is the mass defect. So, the mass defect is basically the amount of mass that we will predict by adding all the protons and neutrons, so predicted mass, and we take away the actual mass. So essentially, the predicted mass is the mass of every nucleon. So nucleons, as we should know by now, are protons and neutrons. So mass of every nucleon, so every proton and neutron. I'll write that just in case. Every proton and neutron. And the actual mass is the atomic net mass number. So basically these two numbers at the top, they're both the atomic masses, net mass number in kilograms. Everything mass related has to be in kilograms for this to work. If not, it will not work. As simple as that. Okay, so now we can actually start calculating. So we know the mass defect. So we know that we need to calculate the predicted mass first, right? So we're going to calculate the predicted mass. So how many? We've got tritium and deuterium. Hydrogen 2 is deuterium. Hydrogen 3 is tritium. Hydrogen 3, we all know, is going to have one proton and 2 neutrons. So we can start by going mass defect. Actually, go mass of tritium equals, so the mass of our tritium, this is going, actually, shit, no, hang on. I really should stop playing this. Mass predicted of tritium, this is going to be this one. Our predicted mass of tritium is going to equal 2 times the mass of a neutron, so we've got 2 neutrons, which is 1.6748 times 10 to the negative 27. The plus 1 proton. And we've got 1 proton, so 1.67252. Hang on. This whiteboard is too small. Maybe I should start doing on bigger ones. Let me know in the comments if you want me to start doing some bigger whiteboards in a slower voice. Let me know. 2 neutrons. Plus a proton. Plus 1 proton, which makes up 2 neutrons, and 1 proton makes up a tritium nucleus. Alright, so now what we do is we go 1.67252 times 7. Now if we actually plug these numbers into... Now we plug these two numbers into our calculator. I'm going to go to calculator. I don't actually have the answer. So just bear with me. Make sure you always put these in brackets. This is the best time ever to start using brackets. So I guarantee the amount of times I've screwed up trying to do these equations just by not using brackets. That's silly, but it's actually so true. You need to use brackets with these. I used to be a noob. I used to be like a dog. I thought, oh, I'm going to do without brackets because I'm a fucking legend, but look what happened to me. I probably got a lot of my physics questions wrong because of these brackets. So please, any maths you're doing in physics, always use brackets. Not just this, but any motion, you always use brackets. Basically from year 9, 8 onwards in school, middle school in the US, from there on, always use brackets. Okay, so now I'm going to get my calculator out. I'm going to calculate this. So what is it? It's going to be 1, 2. Make sure you put a bracket there. Now I'm going to calculate the rest, but always put like bracket and then put your value in there. I'll show you once I got the calculation. Let me just plug it in nice and quickly. It's negative 27 plus 1. So this is what my calculation now looks like. I'll go through it. So this is what my calculation now looks like. So as you can see, I'll put the whole formula in here. So if I press enter, we get 5.02218 times 10 to the negative 27. Times 10 to the negative 27, and that is our predicted mass. The mass of all our nucleons. That is all the predicted mass is. We've done that for these two. So you know what? Actually, we've only done it. That's not our predicted mass yet, remember. I just remembered we haven't done deuterium yet. But deuterium actually won't be much harder from this number. We can do it a much quicker way. So now our mass of that one was 2218 times 10 to the negative 27. That was our tritium. It's the mass of our tritium. Now for fun shit, we can actually, we all know deuterium is tritium but with one less neutron. So we can just grab this and minus the mass of a neutron. We'll just take away a neutron and boom, we've a mass of deuterium. Make sure you always show out your workings. I'm only rubbing them out because I've actually got workings in my book, or partial workings, and also make sure you're very, very careful with using brackets. I know I mentioned a lot, and we're already 10 minutes in. This video I'm not expecting to go for 10 minutes. This video is going to go for 20, easily, because this is a long video. It's going to explain a lot of stuff. So I'm not even worried about keeping it under 10 minutes this video. So deuterium, what we now do, deuterium, essentially grab the mass of the mass of that, tritium, to our deuterium. Deuterium is hydrogen 2, tritium is hydrogen 3. Just remember that, they're just isotopes with names. (27) and we subtract from that. That's actually, that might confuse you guys, that wasn't a division cell, that was more just a general line, so I'll get rid of that. Minus, we subtract the mass of one neutron. You can also just do it if you want. You can always just do the protons and neutrons over again, but this is a much quicker way of doing it. And I'm actually going to prove to you now, it'll give you the same answer. I'm not too worried about going over time in this episode. I'm not too worried. So then we minus 1.6748 times 10 to the negative 27. Here's my calculator. We've got numbers in there, and we got, not much of a difference. Just this number, we got 3.34735 times 10 to the negative 27 kilograms. So now I'm actually going to start erasing these numbers because they're getting everywhere now. I'm just going to write it here so I got the number still. Actually, I've got it on my calculator, don't worry about it. I'll just rewrite it. Okay, now we need to write this number. So our predicted net mass, let's say, is going to equal the mass of our tritium. Predicted mass, I believe, is always going to be more. Actually, I don't believe it is always going to be more than the actual mass. 3.4735 times 10 to the negative 27. There you go. Put that in your calculator. One real quick thing, I'm just going to show you how to calculate deuterium. I'm just going to do it on my calculator. I'm just going to move this back and do it on my calculator, so you guys can see the screen here. So essentially, all I'm going to do is I'm going to do the exact same thing. So, and it should give us 3.3 blah blah blah. So if we add all the protons and neutrons, we've got one proton, one neutron. So it'll be, all it would be is this. I'm going to do the exact way. I'm even going to put ones in the front here. So one. Let's do the proton first. Always use brackets. Plus 1 times 1.67483 times 10 to the negative 27. And you're ready? This game is the exact same number. Yeah. Hang on, camera problems. There you guys will see. 0.34735, 3.4735 times 10 to the negative 27 times 10 to the negative 1. I got the exact same number, that's what I'm trying to say. It gives you the exact same number, so don't worry. We're already 15 minutes in. When I uploaded the Half-Life episode, I just actually increased my I put my phone in, so I can actually upload more than 15 minutes now, so you get to listen to my sexy voice a lot more. So now our predicted mass is going to be those two numbers that are added. So we need to get a new whiteboard marker to equals. Our predicted mass is going to be this. 3.34735 times 10 to the negative 27. And all we do is we add the two numbers. full predicted mass. 0.02218 times 10 to the negative 27. And our predicted mass is going to be actually exactly 8.36953 times 10 to the negative 27. So now we have our predicted mass. So I've got on my calculator, so I'm just going to rub it out. I'm just going to put up here predicted mass. Our predicted mass we just found out is going to equal 8.36953. Do you have to write in all the numbers? Most circumstances they'll give you, not really, most circumstances they'll probably give you something along the lines of, what do you mean? Most circumstances they'll give you something like two significant figures, or three, so 2, 3, it's basically how many places after this. So if they say 2, they want this times 10 to the negative 27. It depends on what the question's asking. Just going to rewrite our reaction up here. So that way now I can put our actual mass here. Just put an A there. Our actual mass. How do we calculate this? You all by now should have done foundation chemistry and know what an atomic mass unit is. If you've done a mole, or a bit of organic and a bit of foundation, if you've looked at moles, you should know what atomic mass units are by now. So I'm assuming you all know what that is. If not, go back and watch the chemistry courses. You will learn heaps. They're not out yet, but when they come out, I'd encourage you to go back to them. Since they're not out yet, I will show you what an atomic mass. That's basically, the atomic mass number is 3U, 2U. Basically, that's just 5 atomic mass units. It's roughly 3 or 2. Well, theoretically, hydrogen, it's 1 hydrogen, normal hydrogen. Hydrogen 1 is 1.008, but we just write it as 1. Okay? You just round the numbers. So it's just another way of saying atomic mass unit. We write it as this little u. Well, that's the way I write it anyway. A little u there. Okay, so what we're going to now do is calculate our actual mass, which is going to be, what's 3 plus 2? Duh, it's 1700. I'm just kidding, it's 5. We go multiply that by, I'm positive at the start of the video, just in case I've forgotten, 1 AMU, atomic mass unit, equals 1.661 times, I think I mentioned it, but I'm going to do it again just in case. There's that many kilograms, okay? So essentially all we've got to do now is just to calculate this, the actual mass. All we have to do, I'm nearly 20-minute mark. Try to keep it under half an hour. How about that? If I run, I've got enough space on my phone. Our actual mass is going to equal, always, it's going to equal, so it's going to be the 5 AMUs. I'll put a little u in there. See, and I'll put a kilograms for the other one too, so you guys actually get it. Times, to convert it into kilograms, we multiply it by that number before. So then what was the number? I just hate working with a small whiteboard. 1.661 times 10 to the negative 27 kilograms multiplied by 5 AMUs. That will give you how many kilograms it is. So remember that is 1 AMU. That's 1 AMU, atomic mass unit. It stands for atomic mass unit. So pretty straightforward. 27, in brackets, multiply that by 5, like I've just done there, and you will approximately get this number. You will actually not approximately yet again, it's exactly this number. It's the exact number you will get. 8.305 times 10 to the negative 27. That's the number you will get. Alright, now, one more thing. The speed of light, before you continue, if you've done motion, I'm probably going to touch a little bit of motion, but not much. Speed of light is a velocity, so you might want to watch the motion when it comes out. Velocity is just speed in a direction. That's all it is. It's a vector. In fact, I've already got lesson 1 of vectors and scalars. It's a vector speed, so it's just a speed. And the speed this is at is 300 million meters per second. That is the speed of light, okay? So 300 million meters per second. Write that down because I'm going to get rid of that. Okay. Now we can actually plug in our formula. Now we know that's... Actually, I could probably leave it here. 3.03, it doesn't really matter. It's always just a decimal. I'm just going to write it simply as 3. We're just broken the 20-minute mark. It's alright. 3 times 10 to the power of 8 meters per second. E is going to equal mc squared. But first of all, actually I missed a step here. You need to calculate the bloody mass defect. Remember what I said at the start? The mass defect or deficit is going to be the predicted mass minus the actual mass. Okay? So let's plug in our, let's say M equals, it's going to be our predicted mass, 36953. I should probably start using these two significant figures, so I'm going to fit more in there. We subtract, our actual mass, which is 8.305 times 10 to the negative 27. This is going to give you still a very small number. So I'm now going to plug this in with brackets again into my calculator. Times 10, if you're having any a bit of background noise, stuff going on in the back. Hey, I'm at a school filming this, so please ignore it. 10 to the negative 27. Okay, so that's going to give you roughly, did I do this right? I think I did, just let me double check. Yep, that's right. That's going to give you 6. So I'm just going to write the answer. So our mass defect, we don't even need these two numbers anymore. I can get rid of pretty much all this shit. So now we're going to have mass defect. You want to know what it is? Well, assuming you've calculated already and doing the questions, you should already know. But for those who are just trying to cheat their way and drop out of high school, this was the number we got. 6.453 times 10 to the negative 29. That should be correct. Yeah, I think that is right. Okay, cool. Speed of light, yet again, is 300 million meters per second. If you watch my motion, I'll teach you how to convert kilometers per hour to meters per second, and vice versa. Now we finally get to use E equals mc squared. So I might go through another example in another video. Actually, I might just go through a real quick example. So I'm hoping you've all done this question before. So E equals mc squared. So M is actually the mass defect, not the mass. In this equation, anyway. That's actually the mass defect, not the mass. Not the mass. It's the mass defect. Okay, so E, we put in our mass defect. Multiplied by 3 times 10 to the 8. 10 to the... Makes that a bit smaller. I hate using this whiteboard. Whiteboard marker's actually worse. Shit, oh well, I've got another whiteboard marker right there. I might as well just use that next time. We'll use it for the next episode. 6.453 times 10 to the negative 29 multiplied by 3 times 10 to the power of 8, and we square that. That's our official equation. Just keep in mind that's E there, so just copy that. Now if you actually want a more simple way to do it, make sure you pause and got that. Always pause if you need to get something. Number 1 tip. Okay, so now what I'm going to do is this. Let's get this a bit. This is what we now do. Always, my opinion, the way I do it, this speed of light bit, I never put in this into equation. I never put in this. Actually, I'll draw that bit straight. I never, ever do this. Keep in your mind that that is always going to equal 9 times 10 to the power of 16. Just remember that C squared is that. Just remember that. It is so much easier than doing that. You save a bit of time. Oh, no, you fucking kidding me. I rubbed out the mass defect. Oh wait, thank God I've still got it on my calculator. Thank Christ, I must have had to do video editing. Alright, still got it on here. Mass 6.5 kilograms. And C squared, keep in mind, is what's 9 times 10 to the 16 meters per second. So, I know you really can't, no, just 29. leave that as 9 times 10 to the 16. I'm going to try and make it under half an hour this video. This is a long video. Now, we get to use the formula. Sorry, I did say before, but now we get to use it. E is going to equal C squared, 6.453 times 10 to the negative 29 times, let's multiply it by 9 times 10 to the 16. You could do it 3 times 10 to the 8 squared, but that would give you the exact same answer, and it's much quicker to do it this way. So now we finally calculate how many energy we have. And we have officially got quite a lot of energy. Damn son. My friends, we have a bit of energy here. So the amount of energy in joules, we've still got to convert to electron volts. So yeah, stay tuned. Remember I said at the start, electron volts. The energy we end up getting is 5.8077 times 10 to the negative 12. You might go, was Einstein originally planned this so you could use big numbers? But that's a really small number, right? How do we get to a bigger number? That's where the electron volt comes in. Now, fun fact, 1.6 times 10 to the negative 19 is the charge of a single electron, whose charge of 1 E minus, or 1 electron. Right, that's it. That's all that number is. It's basically given that to electron volts or electron joules. It's called electron volts. There's no such thing as electron joules. Okay, we now got our energy. Now there's 2 neural units, so I wrote this at the beginning, but I'm going to write it again. Equals 1 electron volt, 1.6, I'm getting tired now, times 10 to the negative 19 joules, and then 1 MeV, I believe it means mega or million electron volt. I actually don't know, and I'm really sorry, I should know that if I'm teaching you guys. Equals a million electron volts. There you go. Okay, so now I've still got the number here. We do not need any of this anymore. So let's just write our reaction. So you keep that up here, and let's also put the equals MC squared back on. Bloody hell. Plus 1 neutron E C squared. I'm going to try to keep this half an hour. We're at 27-minute mark now. Okay. Last step. I'm not going to do a second question. I really can't bother. I'm going to do more lessons. So yeah. Essentially now what we do is we do this. Now we have our our energy, which is... I know you guys can see the calculator in the shot. Joules, yep. Okay. Now how to convert it to electron volts? We do this. Putting in brackets first of bloody all. Call me Professor Bracket in a sec. Now you divide that by 1.6 times 10 to the negative 19, and we said that's 1 electron volt. So if I theoretically plug that in, I'm going to do... What I'm going to do is this. I'm going to do this. Times 10 to the negative 12. Oh, whoops, I did it wrong. Apologies. And we divide that by 1.6 times 10 to the negative 19, we actually get a non-notation number. So an actual number this time. Well, these are numbers. One that's actually not in scientific notation now. Get rid of the equals squared. Oh, sorry. Sorry. Alright, now, the last few steps, we're nearly done here. All we're now got to do is we got our energy, which is now, we already had it, 362.98125. So that is 36 million electron volts. But you might say 36, isn't that going to be like 36.2 something? You're right. Now we convert it into MeV, and then I promise you that is it. Divided by 10.6. So you just do this. And it's divided by 1,000,000. 10 to the power of 6 is 1,000,000. Your final answer. I'm about to break half an hour. 36.298.125 mega electron volts. And there is your answer. Let me write that. There you go. By all means, use this video as a guide, because it's a very long process. I'll try to put as much resources as I can on Dylan teacherscience.x10host.com. I'll put as much on there as I can. Thank you. I've just hit half an hour. Thanks for watching.